On to section 1.7 and a look at categories. Some of the topics will be products, coproducts, and free objects. Category theory. I really doubt you covered this in senior level algebra. Could be viewed as a bit of a peripheral topic, though Hungerford emphasizes it a bit more than some other algebra books. Now, the first 6 sections, those contain topics you probably did see in undergraduate algebra, senior level algebra. We've done them certainly in more depth in this graduate class. The remainder of chapter 1 contains topics you probably didn't encounter at all in a first algebra class at least, possibly in a second one though. Hungerford uses terminology from the area of categories in the rest of chapter 1, not extensively, but somewhat. And it's occasionally sprinkled throughout the rest of the book. Actually, the last chapter of Hungerford, chapter 10, is all about category theory. It's only about 20 pages of it. If we were to compare this, say, to Dummett and Foote's abstract algebra book, kind of a rival to Hungerford, category is mentioned here and there in the body of the book, but there's not a chapter devoted to it. There's an appendix devoted to it in that book. So let's do a little bit of this category stuff. What we're doing is moving kind of beyond the idea of a set. When we talk of categories, sets have their shortcomings, as you know from your previous exposure. So informally, a category is a class of mathematical objects. We might talk about the category of groups or the category of sets and so forth. Russell's paradox shows that we can't have a set of all sets. The axioms of set theory lead to contradictions if you try to speak of a set of all sets. But we can have a category of all sets. Some of this you might find in more depth. There's a book by Saunders McLean on categories for the working mathematician. It's from 50 years ago. But there's a reference for more details on that. The idea is to collect into a category all similar mathematical objects, and then to give a proof of some property in the category setting. Well, if it holds in the category setting, then it holds in any setting which can be described in terms of category theory. Jumping to chapter 10, just to get a motivational paragraph from Hungerford, more to elaborate on what we just said. Quoting Hungerford, chapter 10, page 464. Many different mathematical objects may be interpreted in terms of categories, so that the techniques and theorems of the theory of categories may be applied to these objects. Consequently, it is frequently possible to provide a proof in a category setting which has as special cases the previously known results from two different areas. This unification process provides a means of comprehending wider areas of mathematics, as well as new topics whose fundamentals are expressible in categorical terms. So it's a generalization that allows us to consider broad categories of various objects under sort of an umbrella idea. And that's what math is often about, is to generalize things and prove general results that are unifying in a sense. So the idea is to have this category concept as a unifying concept from different areas. Now, formally, here's what a category is. It comes in several pieces. A category is a class C, calligraphy C, of objects. We'll usually denote the objects with capital letters, together with a class of disjoint sets denoted Hom AB, one for each pair of objects in the category C, and an element of Hom AB will often denote with lowercase letters. It's called a morphism from A to B, and we'll denote it morphism F maps object A to object B. So we're referring to the things in a category as objects. So I'll try to stick to that verbiage. And these are, they're by definition nothing yet, but of course there'll be mappings of some sort from from object A to object B. And part two, in a nutshell, part two lets us take compositions of the elements of Hom AB. So for any triple of objects A, B, and C, a function, it's the first time we've used that word. Morphisms, we didn't use the word function, though we did use function notation, and we're trying to compose these things. So we're certainly treating them similar to functions. But here we're actually explicitly saying function that maps the Cartesian product of Hom BC with Hom AB to Hom AC. And this function mapping that takes an ordered pair of these things here to a thing there is called a composite of the inputs. So more explicitly, we have the notation. If we have a morphism in Hom AB, then we'd say F, just read this in a traditional way, F maps A to B. An element G of Hom BC would mean G maps B to C. And with this mapping, notice the codomain, the output of F, is the same as the domain of G, and I shouldn't be using those function theoretic terms in this setting of morphisms, but give me a little break on that. This is a prime setting for some kind of composition. So what we'll do in that case is say we're associating with the ordered pair. Notice the G comes first and the F comes second in the ordered pair. Of course, it's because we're going to take G and compose it with F. So in the composition, F comes first and G comes second. And sure enough, if you will, the domains and codomains line up then. But we're requiring that we have a function that takes ordered pairs as given here and produces another thing as given here. We'll denote the fact that with ordered pair, we associate an element of Hom AC, and we'll denote that element is G composed with F. G composed with F maps A to C. In other words, the composition, the composite of those two is given here, and composite is the common term. So we have a composite of F and G, a composition of F and G. In addition to that, we require that these composites satisfy the following. We have associativity and there's an identity. So if with the proper mappings, proper domains and codomains, if you will, so that we can take a composite of three functions, H composed with a composite function, G composed with F, is the same as H composed with G, and then take a composite with function F. In other words, you can move the parentheses around. So we're requiring in a category that we have this kind of associativity with compositions of these elements of Hom, these morphisms. And for each object B of C, we require that there exists a morphism 1 sub B, mapping B to itself, such that for any function F mapping A to B and any function G mapping B to C, we get this kind of composition. Okay, morphisms are not functions, despite my innermost desires to refer to this as an identity function. It's not a function, it's a morphism. So functions we can define on sets. These are not sets, these are objects in a category. So there's some of the technical details. But we're requiring the composition 1 sub B with F to equal F and the composition of G with 1 sub B to equal G. By the way, notice that the domain, codomain things make sense. If we took F composed with this 1 sub B morphism. F would take us from object A to object B, and then this would address object B. It would map B to itself. And similarly over here, the 1 sub B comes first, so it takes in B, gives out B, and then G takes B and gives out object C. So the domain, codomain stuff lines up, and that's what a category is quite formally. So to establish something as a category, we need this existence of the 1 sub B's on object B for any object in the category. We need the morphisms when they compose to compose in an associative way. We need a definition of a morphism composition, and we need the collection of morphisms. So that's what a category is formally. First, before we do an example, definition of equivalent, we'll use this a bit. We'll use this in our first proof in particular. In a category C, a morphism mapping A to B is called an equivalence if there is in the category a morphism G mapping B to A, so the mappings are in the reverse direction, such that G composed with F equals 1 sub A, and F composed with G equals 1 sub B. So if F is an equivalence, then A and B are said to be equivalent objects. Okay, so this looks for all the world like a composition of functions that give the identity function. It's not, it's a composition of morphisms that gives these particular morphisms. But equivalence will play a big role. Let's go for something a touch more tangible. Let's talk about sets and groups. First example, let calligraphy S, I'll use calligraphy fonts to indicate these categories. Let calligraphy S be the be the category of all sets. For A and B and S, Hom AB, take it to be the set of all functions, F mapping A to B. Okay, I can define functions on sets. Morphisms are, in general, a different kind of object, but here we're talking sets, and here we're taking as functions the morphisms. Function composition is associative. Yeah, that's old news. You know, function composition on sets is associative. So we've got the associativity. We need the kind of the identity type stuff. If we take any object B, here B would be a set. We can define the 1 sub B morphism simply as the identity function on set B. That'll give you the identities. That'll give you, that'll give you the 1 sub B's for any object B. And that'll give you the associativity you need. So we've got composition. We got composition of functions. So we have composition of morphisms, and it satisfies the associativity in this 1 sub B property. In terms of equivalence for sets, we'd have equivalence if we could do a composition and get these things here. In the set theory setting, these things here are identities. And by the way, that's the same notation that Hungerford was using for an identity function on set A in the past. So we know, I guess it's section 0.3 from some of the background material in chapter 0, when speaking of functions. If I can get G composed with F as functions on sets to equal the identity on set A, and F composed with G to equal the identity on set B, then this function F, as well as a function G, is invertible, and so it must be a bijection. So in this example of a category, equivalences are given by bijections. So in this categorical setting, we have that two sets are equivalent, not equal, Two sets are equivalent in this category if there's a bijection from one to the other. That means they're the same cardinality. So when dealing with the category of sets and these particular morphisms, equivalence means same cardinality. Equivalent sets in this category with these morphisms are those which have the same cardinality. We'll make a comment about that here a few lines down as well. Let's try it with groups. Let calligraphy G be the category of all groups with Hom AB is the set of all group homomorphisms mapping A to B. So one thing, homomorphisms are mappings of one set to another. You're mapping the elements of group A to the elements of group B. So associativity and identity, we get that because these are set mappings. We get that from the previous example. The thing about an equivalence we're interested in, so let's look at the definition of equivalence again. It's still nearby. Equivalence means compositions in this sense give identities. In theorem 1.2.3, part 2, I just happen to have it sitting here. We said in part 2, F is an isomorphism if and only if there are homomorphisms, F inverse mapping H to G such that the composition of F with F inverse equals the identity and the composition of F inverse with F equals the identity. Back from section 1.2 where we're talking just regular old functions and not morphisms. But we've created a setting, a category, where the morphisms are regular old functions. So this F inverse is playing the role of G, and we want to know when we get an isomorphism. We get an isomorphism if and only if we have that kind of composition. Was the claim of that result. And that was exactly what we had here. We use a symbol F inverse instead of G, but that's exact same thing we have here. So in this example, category of groups, we have the morphisms given by homomorphisms, and I'm trusting that's motivation for some of these symbols. And we have an equivalence if and only if we're dealing with morphisms, which are, in this setting, isomorphisms, group isomorphisms. We could restrict this to a billion groups and do some similar things, of course. But what we get then is, in that category, two groups are equivalent if and only if they're isomorphic. So in the two examples we had, sets were equivalent if they have the same cardinality, and groups are equivalent in this category if and only if they're isomorphic. So that sounds like a reasonable example of a category. Yeah, two groups are equivalent if they're isomorphic. They're structurally the same. How do you feel about the set thing? Two sets are equivalent if they have the same cardinality. What's the structure of a set? Sets don't have a structure. They just got a bunch of elements. So I usually say, in its broadest sense, an isomorphism is a one-to-one and onto mapping that preserves structure. That could be the case in vector spaces, in groups, graphs. In a graph, the structure is connectivity, adjacency. But sets don't really have any structure. So you never talk about isomorphic sets. You might talk about one-to-one and onto mappings, bijections between sets. And the only thing you could preserve is the cardinalities of those sets. So it makes sense to say that two sets are equivalent if they have the same cardinality. They don't have any other kind of structure. All they got is a cardinality. So that's a reasonable thing as well. And in this particular example of a category, that's exactly what happens. We can come up with a somewhat different example based on a single group. So to illustrate that a category need not consist of all sets or all groups, consider a group G, let's use multiplicative notation. A single group G can be considered as a category with one element. Now, we would need then the Hom G comma G. We need to define that. So we'll define that as mapping the pair, the ordered pair A, B, to a binary operation B. So we're using the binary operation in the group to define this composition. The 1 sub G would simply be the identity. Of course, if we take the identity in the group, that's going to compose in an appropriate way with all the elements of that group. Every element in a group has an inverse. So every element is an equivalence. The elements are the morphisms themselves. If I take a group and multiply it on the left by a single element, it really permutes the elements around. The multiplication of elements under the binary operation ensures all that other stuff that we have a category. Yeah, you've got the identity stuff. You've got the associativity, right? Binary operations in groups are associative by definition. So there's a slightly more, actually really more exotic example of a category. Okay. What we're going to do now is shift from a category of objects, which we'll start with a category of objects, and define a new category based on the morphisms of a given category. Okay, so we need a bunch of details to check in all this stuff. Fortunately, it can largely be dealt with in terms of some diagrams. So let C be a category. We're defining for category calligraphy C a new category, calligraphy D, whose objects are all morphisms of C. If we have morphism F mapping A to B and morphism G mapping C to D, then Hom FG consists of, so now we're defining what the morphisms are in D. Hom of that ordered pair FG consists of all pairs alpha and beta of morphisms of C such that alpha maps A to C and beta maps B to D. And when we compose F composite beta, F compose with beta, that's the same as alpha compose with G. Both map both map object A to object D. Okay, in other words, here's what's happening. So we started with a bunch of objects in C, so A, B, C, and D. In C, we would have a morphism that would map this object to that object, maps A to B. We'd have a morphism that maps this object to that object. We'd also have the alpha and beta morphisms. So we're considering the pair alpha beta. Alpha beta, we're considering this pair of morphisms, ordered pair of morphisms from category C. And we're going to use the pair alpha beta to map morphism F to morphism G. Let's try that again. So we start with a category, calligraphy C, that has object A and object B in it, and a morphism maps A to B. We're trying to find a way to map the morphisms of C to other morphisms of C. So we're going to map morphism F to morphism G using the ordered pair of morphisms from C, alpha comma beta. If you will, alpha maps the domain of F to the domain of G, and beta maps the codomain of F to the codomain of G. So we're going to use this alpha beta, it's given at the bottom, this pair alpha beta to map morphism F to morphism G. So the objects in calligraphy D, the new category, are the F's and the G's, the morphisms from the first category. And the morphisms in the new category are ordered pairs of morphisms from the old category. See, the only little part I didn't discuss in the diagram is we require F composed with beta to be the same as alpha composed with G. F composed with beta, that'd be, let's see, F composed with beta maps A to D. Oops, there's a little typo. That should go the other way around. It should be beta composed with F. Yeah, the F comes first, followed by the beta. Yeah, a little typo there. We're mapping A to D, and what we get is commutativity. F composed with beta is the same as alpha followed by G. So we'd have here, my composition's messed up here. We'd have beta first. If I wrote it like this, yeah, that's wrong. I think I got both of these backwards. You know, what we're trying to say is when I map A to D, so that would be F followed by beta, and that's backwards with a function composition notation, is the same as alpha composed with G. Yeah, a little concerned with that. I think I've got both of those backwards. Of course, these are morphisms, not functions. Maybe I will correct the notes as appropriate, so I'll double check that. But the idea is we've got commutativity in this diagram. If we follow this branch from A to D, or we follow that path from A to D, we get the same mappings. So in terms of the compositions, I think I've got both of those backwards, but I do need to think on that. But a lot of this will just depend on the diagrams being commutative. But we're using this pair of morphisms to map that morphism to that morphism. And all it does is patch together these four morphisms in such a way that we have a commutative diagram. That's the last condition up here in terms of the same mappings. So if these conditions are satisfied, then we consider alpha beta mapping F to G. Order matters, right? It's sort of a domain versus codomain thing in terms of where the mappings are. Alpha maps the domains and beta maps the codomains, if you will. Associativity, okay. Let's deal with associativity in terms of a picture. So to check associativity, we'd have to have three morphisms. So our three morphisms in category D are ordered pair alpha beta, ordered paired gamma delta, and ordered paired epsilon kappa. So the plan is, as we had previously, the pair alpha beta maps morphism F to morphism G. The pair gamma delta maps morphism G to morphism H, which is the same thing we had before, just different symbols. And finally, morphism epsilon kappa in category D maps morphism H to morphism K. And we get into this situation by having a bunch of commutativities. I want to go from A to F. I could either go, over and down, down and over, down and over. We've got all those commutativities that will allow us to weave through the diagram in any path you like, directed path for those fans of graph theory. So what we want to show is the composition of alpha beta with gamma delta, followed by a composition with epsilon kappa, equals a composition of alpha beta with the composite gamma delta with epsilon kappa. We're trying to show associativity. And it's the commutativity of the diagram that gives it to us. So I think I will let some of this lie. And indeed, we get composition of a composite function is the same as a composite function composed with the alpha beta. Order matters, of course. Order is going to matter big time with this stuff, but you do get the associativity. And it's simply a matter of is the same as, right? We're getting a lot of the is the same as, if I've got my compositions in the correct orders here. We get a lot of that because we've got a commutative diagram. We've got arguably three commutative diagrams sort of pasted together, one for each of the morphisms that we're defining in category D. So we have the associativity, we have morphisms defined, we have compositions defined. Identity is the only thing left. And the plan will be, again, let's look at it in terms of just some diagrams. The plan will be, we'll take mapping from A to itself. We'll denote that as iota sub A. Sometimes that's done in the symmetry groups. And we'll take the mapping from B to itself. Such mappings must exist. I don't want to call them identities. They're mappings that compose with other mappings as if they were identities. So what we need then, we're trying to map, we're trying to get a composition that will behave we're trying to compose this ordered pair with this ordered pair and show this behaves like an identity. We're trying to take alpha beta composed with the iota sub A, iota sub B, and show that that behaves the same as the mapping alpha beta. So we're trying to take alpha beta composed with that what's alleged identity and show that we get the alpha beta back out. So indeed, this is behaving as a left identity. Commutivity of the diagram will tell you if I follow along this path or follow along this path. Again, the A to D kind of stuff. We're getting the same kind of behavior as we would get by following on to an abbreviated path. The composition behaves as it should, and indeed, this thing here is behaving as, what's this, an identity when composed on the right. No, I shouldn't say identity. It's composing in such a way that we get this kind of behavior. If we go to the other side with that iota sub alpha, iota sub beta thing, and try to use it in a composition in this setting where we've got it over here on the other side, well, now we'd need the mappings to come into A and come into B so we can take the composition and get it on the other side. And that is given here. And the commutivity again of the diagram will produce that we get the same mappings. In other words, we could define this 1 sub alpha beta to be this iota sub A, iota sub B. This being, so desperately want to call it the identity, this being a morphism that acts as an identity in category C, and the pair of them being a morphism in category D that acts as an identity. So the diagrams give the ideas. Okay, we're going to shift gears a little bit and talk about products. And one of the first places we're going to use this category theory stuff is when we define products of groups. So let's try to make some sense out of this. Let C be a category, A sub I ranges over indexing set capital I. So this could be a huge collection. Let this be a family of objects of category C. A product of the family. Okay, so we start with a category. We pick a family of objects in the category. And that's the thing of which we're taking a product. So we're defining a product of, I'd like to call it a subset, but I can't do that. Well, of a family of objects in category C. The objects subscripted capital A's. So a product of the family is itself an object of C. So that's a bit of a requirement there. Together with a family of morphisms, pi sub I, that map that product to each A sub I, one of those for each index, lowercase I and capital I, such that for any object B in category C, and any family of morphisms, phi sub I, that maps B to the A sub I, there is a unique morphism, uniqueness, something we'll either be able to use or we'll have to establish, depending on if we're in a category or showing that we have a category. A unique morphism phi mapping B into the product such that the composition pi sub I with phi is equal to phi sub I for all values of the index. We'll denote that product, I think most illustratively, as P is the product of the A sub I's over the indexing set. We'll also occasionally use this notation. Initially, we'll use this a little bit. So product, it looks like it's being based on the pi sub I's. Okay, let's try to make some kind of informal sense out of this, and I will struggle, I'm sure, myself with this a little bit. So we're defining this product, and we're requiring it to behave as follows. We've got, ultimately, we kind of got like three different things. We've got the A sub I's that make up the product first. Secondly, we got the product itself. And thirdly, we've got object B. Could be anything. So any object B. And we've got an interaction of the P's with the A sub I's and the B's with the A sub I's. And over here, the B's with the P's. So it's all about these mappings, these morphisms. So what we're saying down here is we're getting this phi sub I and having it behave in a certain way as a certain composition. So the story is the phi sub I's take object B, right? First comes object B, and then comes the family of morphisms that map the B's into the A sub I's. So the phi's are mapping the B's into the A sub I's. So that's what this composite must be doing. But the composite is phi first, so that takes B into P, and then pi sub I. Well, pi sub I takes P into A sub I. So the composite runs B through product P and then to A sub I. So what the phi does is allows us to take this mapping from B to A sub I and kind of run it through the product P. And that's exactly what happens in terms of the compositions. So that's about as good as I can do at motivating this definition of a product thing. We'll not do this in today's video, but something called CoProducts is on the horizon as well. So we'll reverse some things when we do CoProducts. Let's explore this idea of a product of objects in a category a little bit more. We've required the product itself to be an object in the category as part of the definition. Object P of C. So the requirement in the definition is that the product itself is an object in C, given right there. So a family of objects in a category may not have a product. You may not be able to do this in such a way that the thing you define is actually an object in C. But anyhow, so claims Hungerford. Products do exist in the places that we need it to. Products of sets exist. They're simply Cartesian products. And you've dealt with Cartesian products, and you know they can be done over any indexing set. Theorem 0.5.2 gives some results concerning Cartesian products. The existence of a Cartesian product established on axioms of set theory or something to that effect. We're interested in products of groups. So we want to take an arbitrary collection of groups and define a product of those groups. That'll be done in the next section. So, and it'll refer to this category stuff somewhat. Another little comment, which I largely want to explain in terms of a picture. If we take a couple of indices from the indexing set, you kind of want to think of, say, A I sub 1 and A I sub 2. Maybe think of them as parts of the product or factors of the product. If they're calling it a product, something like this ought to be the case. If we have morphisms, pi I sub 1 and pi I sub 2, that take the product and map it to these parts, these AI sub 1s and AI sub 2s. If we're in a category and the product is also an object in the category, then such morphism should exist. So we need then for any object B and C, so we're doing that any object thing, which is related to compositions, any morphisms, phi sub I1 and phi sub I2 with appropriate mappings. Let me not read that to you. Let's look at it in terms of a picture. We need there to exist a unique morphism phi that satisfies the following conditions. So we'll have P, and these pi's, kind of think of them as projections. I think of them as projections. I use pi. It's projecting the product onto a piece of the product in some sense. But we get the pi sub I, pi I sub 1, pi I sub 2 that maps us to I1 and I2 respectively from the product. And then we've taken an arbitrary object B and a collection from B, collection of morphisms, to AI sub 1 and a collection of morphisms to AI sub 2. And we're requiring on that composition condition above that B, that this diagram commute, that B mapped by phi to P and then by pi I sub 1 to A I sub 1 is the same as the mapping from B to A given by phi I sub 1. And similar behavior over here. You're requiring commutativity of this diagram. That's what this composition stuff means. So ultimately, this composition stuff is some kind of commutative diagram stuff. In general, we're requiring this diagram be commutative over all indices, right? All I1s and all I2s and all pi sub i's and all phi sub i's, and the B is arbitrary as well. So there's a bunch of moving parts potentially in that definition of product. What we're about to show is there's a little bitty bit of independence where we get some freedom in the choices of these pies that project the product onto the parts of it, as I've called it. So the following result shows that the construction of a product is independent of the pi sub I morphisms, independent of these things at the bottom. So at least there's that. The statement is, let C be a category of objects, A sub I from some indexing family, a family of objects in C. We're defining product, this is that alternative notation, a product P of those objects using the pi sub i's in the definition. And we're also defining Q as a product of those objects, but this time using psi sub i's. So we're taking pi sub i's and psi sub i's, and we're taking different collections of those projections and showing doesn't matter. So we're going to show then that product P of these objects and product Q of the same objects these two products are actually equivalent. All right, one more time. What's equivalent mean? It means a mapping. Go back to the previous page. I'll go back a couple of pages. Go back several pages. Here it is. Being equivalent means we get compositions that give identities. Compositions in two directions that give identities. In that case, then objects are equivalent. So we want to show the object, the products, P and Q, are equivalent. We want a mapping, or mappings F and G, that compose to give an identity. So that's how we'll show equivalence. Back to the statement, actually onto the proof. So we need mappings from P to Q that compose to give the identity, mapping from P to Q and a mapping from Q to P. The proof is actually not terribly complicated. The verbiage, a bit of a mess, but we're trying to show equivalence of these two products. Okay. P is a product, Q is an object in C, psi sub I, that's Q, to A sub I. So knowing that the product exists, we know there exists a unique morphism, G, mapping Q to P, such that we get this kind of composition. This is treating Q as the arbitrary object, capital B. And we had then that unique morphism G based on B that compose with the pi sub i's to give, in this case, psi sub i's. In other words, what we're getting here is, it's the one on the right because we got compositions with G. We've got G composed with pi sub I behaving the same as the psi sub I. So we're making explicit use here of the pi sub i's and the psi sub i's. Based on that, we want to construct an equivalence and conclude that P and Q are equivalent. Similarly, if we interchange the roles of P and Q and replace F with G, I guess if we interchange these roles and think of Q as the product and P as an object, then with these pi sub i's projecting P into A sub I, there's a unique morphism, let's call it F. So up here we get a unique morphism mapping P to Q, and we get the same type of composition. F followed by psi sub I is the same as these P sub i's. Okay, the very definition of what it means to have a product. So we've assumed both of these are products, which assumes they are categories. I'm sorry, they are objects in the category itself. And then the rest of this is just treating those products as objects. Well, one of them is an object and the other one is a product, and then interchanging their roles. Here's what we're going to do next. The centers are the same. I've intentionally drawn this in a particular way. The Q's are the same, the psi sub i's are the same, the A sub i's are the same. So let's glue these together. Thing is, up top, if I glue these together, we can go from P to Q, or through Q, and then back to P. Let's treat this as F composed with G, mapping P to itself. And so we're doing a composition of these two functions. We'll drop this, we'll drop a Q, and take a mapping straight from P to itself. So we'll get a mapping straight from P to itself. It was F first and G second, so the composition, I guess, looks like this. We had the pi's on the side, and the Q is gone. So we've got this G composed with F, maps P to itself. It's a morphism, and it has to satisfy certain composition properties. We had the commutivities of the previous diagrams. We'll have it here as well. We've got, let's see, G composed with F pi sub I, so go from P to P with G composed with F followed by pi sub I is the same as pi sub I. This diagram commutes. So that occurs and must hold for all indices. So the product based on the pi sub i's, it's an object. Pi sub I maps the product into the A sub i's. That means there's a unique, here we're using the unique morphism thing. Again, there's a unique morphism that maps P to P where we get this kind of behavior. The choice here is unique because we're dealing with a product. Well, the identity works, the 1 sub P works. There is that mapping, 1 sub P, that takes P to itself, and we'll have the composition behave in such a way that pi sub I composed with 1 sub P will equal pi sub I. But if we have a unique morphism that behaves like that, and 1 sub P behaves like that, and G composed with F behaves like that, then we have G composed with F equals 1 sub P. And that's halfway there. So we wanted to show that G composed with F equals 1 sub P, and F composed with G equals, I think that'll be 1 sub Q if you look at the domains and codomains. But that'll be exactly what we need to show we have an equivalence. So let's do the same stuff, except let's interchange the roles of P and Q. So now we've got the Q's on the outside, the P's in the middle, the pi's and the si's, I guess, have to be interchanged as well. So now we have this kind of mapping. Do the same thing. Sort of merge these two together, no problem at the bottom. Got the same thing, no problem. With these mappings, we've got the same thing. A little bit of a problem here. If we're going to remove P, I need to deal with this as a composition. G comes first and F comes second. So I think we get these in the opposite order. Now we get F composed with G before we had G composed with F. And what we would find is we've got commutivity here. But remember, this can be chosen in a unique way, as we did on the previous slide. And the mapping, the morphism, 1 sub Q, would also yield a composition that's the same. 1 sub Q followed by psi sub I would equal psi sub I. So as we had on the previous slide, same thing, except F and Q are in the opposite, F and G are in the opposite order, and we don't have 1 sub P, we have 1 sub Q. So now we've got G composed with F equals a 1 sub P, F composed with G equals a 1 sub Q. That's exactly what an equivalence was. So product P, product Q, these are equivalent, and we don't have to worry about these things I've been calling projections. We don't have to worry about these pi sub i's and psi sub i's. It's independent of a choice of those when defining a category. Well, independent up to equivalence, which is the existence of a certain kind of mapping. Okay, so let's pause it there. We've still got some other stuff to explore. We need to explore coproducts versus products. We'll reverse some directions of mappings when we look at coproducts. We need to look at something called concrete categories as a topic that remains in this section, and what it means for an object to be a free object on a set. We'll use the product stuff when we talk about products of groups in general. The coproduct stuff, I think, arises in that same setting. And free objects lies in our future because, and I think it's in section 1.9, we'll look at free groups. So let's take a break with that, and we'll come back and finish the other half of section 1.7 here any minute now. Have a nice day. See you soon.